Okay, so ladies and gentlemen, welcome to this seminar. First of all, many thanks to Professor Fano for this very kind introduction, and welcome to this seminar. I'm really very happy to have the opportunity to talk to you. Let me also say in advance, I would have loved to meet you in person in Urbino. This was not possible on this occasion, but I'm confident this will become available in the near future. Let me say, I know some of you already know me. For those of you who don't know me, I'm associate professor in the School of Business of the University of Leicester. And I'm a physicist. I was trained as a physicist, and I've been interested in the first part of my academic career in the mathematical and logico-epistemological foundations of quantum theory as a physical theory. And then I became interested in collaboration with the Free University of Brussels of Diederik Arts, as correctly Professor Fano was mentioning. I became interested in the application of quantum structures, so the mathematical formalism of quantum theory, detached from its physical interpretation to cognitive phenomena, to cognitive science, in particular to judgments and decision-making under uncertainty. And so, because we realized that several problems that are long-standing problems in cognitive science can be solved at once if one adopts a methodology originally employed to represent microphysical systems. So this is so in this seminar I'm going to present let's say my personal research trajectory. And just some bits of information before starting. This is my staff profile. Let me say, I'm not sure whether this webpage is still available because I was informed by the University of Leicester that they are changing the structure of staff profiles. So I don't know whether the new one is available. On the second part of this slide, on the contrary, you will find so an acronym, which is IQSCS. It's the acronym for Center for Quantum, Social and Cognitive Science. This is a research center I've founded in 2014 together with my colleague Emmanuel Haven, who was at that time at the University of Leicester. And so these the topics we are going to discuss in this seminar, but additionally many other topics are developed in detail in the center. If you have a look at the members of the council, you will find outstanding scholars, including Marisa Dalla Chiara and Professor Beltrametti. And let me also say that I'm proud to say that the activities of the center, IQSCS, will be presented in a movie which will be projected in the next meeting of the American Physical Association. The American Physical Association, APS, is the association which publishes Physical Review Letters, Physical Review X, and other physical review journals. So we are proud about that, that we will go into that meeting. So having said this, this is more or less the content of this seminar. So I will split into a few parts. So I will start by presenting the limitations of classical structures in the modeling of cognitive phenomena. Then I will go into the so-called quantum cognition research program. There is even a Wikipedia page dedicated to quantum cognition. And I will, more precisely, I will go into details regarding origins, motivations, and I will deal with a couple of applications of quantum structures to known cognitive fallacies. Psychologists call them cognitive fallacies. There are two classes of two main classes, as we are going to see in this seminar. One of them are called probability judgment errors, and the other are called decision-making errors. So the third part of this seminar will be dedicated to convince you that quantum structures work better than classical structures in dealing with this kind of complex cognitive phenomena like judgments and decisions. So I'm not sure whether I will be able to cover everything in the time that Pierluigi gave to me, but I will do my best. So let me start by this classical structure, by this slide. So this is well known, what I'm going to tell you in the next few slides. So set theoretic algebraic structures, for example, Boolean algebras, are considered the building blocks of classical logic and classical probability theory. So these structures were originally used in classical physics, and then they were so successively applied to a variety of disciplines. I'm talking about them as mathematical structures, okay? So algebraic structures. So they were applied to psychology, economics, finance, computer science, statistics with very good results. So there are reasons to call them to refer to them as classical structures. In particular, this is probably less known, Kolmogorovian probability models have characterized the experimental revolution which occurred in cognitive psychology in the 70s of the previous century. Now, just for the sake of completeness, I reported the definition, the main definition I will rely on. So I'm sure you know what a sigma algebra is. So the idea is that we can deal with the sets. So we can, in a sigma algebra, we can compose sets. And we can talk about the distributive property. And we can define a normalized probability measure on a sigma algebra, which typically satisfies these two conditions, normalization and additivity, conditions which were introduced by a Russian mathematician, Andrei Kolmogorov, in the 30s of the previous century, who put probability theory, classical probability theory, in an axiomatic form. So this is why classical probability theory, which is probability theory, which can be traced back to Laplace and which we teach in our courses. I'm exactly talking about the probability theory which comes to our mind if we have not studied, let's say, quantum physics. So this probability theory is also called Kolmogorovian. So I will refer to it as Kolmogorovian because it was axiomatized by Andrei Kolmogorov firstly. We know also that the elements of a sigma algebra denote events of the real world. So we can talk about probability of events in Kolmogorovian probability. We can introduce the notion of conditional probability. We know that Bayes' formula holds regarding conditional probabilities, and then one can easily derive these two laws, which I wrote in the second part of this slide. So the first is the law, the so-called law of monotonicity, the probability of let's say, the conjunction of two events has to be less than the probability of each individual events, the component events, and this corresponds to a law of monotonicity for the conjunction. We have a law of monotonicity for the disjunction of two events, which is what I write in the right side of the first equation. The second law is the law of total probability, which again can be easily derived, and where you know that the prime denotes the complement of a set. You may ask, why are you talking about these simple laws of Kolmogorovian probability? Because people don't use these laws as they should be used. Indeed, so growing evidence reveals that these classical structures, when applied to complex cognitive processes like judgments and decisions, lead to predictions which do not agree with empirical data. In this sense, we talk about violation of classical structures. And empirical literature in cognitive psychology has identified two main errors, let's say, so two main classes of phenomena where these two laws are violated. So the first class corresponds to a violation of the law of monotonicity and goes under the name of probability judgment errors. Given two events E and F, people judge the conjunction event E and F as more likely than the events E and F. E or F, depending, in some cases it is greater than both. So, and you have a symmetric effect for the disjunction of two events. So people judge the disjunction as less likely than the individual events. And you have a second class of cognitive phenomena where you find empirical deviations and which go under decision-making errors. So given two actions, F and G, people prefer F over G when they know that an event E occurs, and also when they know that E does not occur. So when they are certain about occurrence or not occurrence of the phenomenon, but they invert their preferences, preferring G over F, if they don't know whether E occurs or not. If we put this probabilistically, you have a violation of the law of total probability. So there are many examples in the literature of this type. I will in particular, regarding probability judgment errors, deal with over and under extension effects in membership judgments on conceptual combinations, and also I will deal with the so-called conjunctive and the disjunctive fallacies. Probably some of you have heard about the Linda story problem, but if not, I will come to it in a few slides. I'm not sure whether I will be able to sketch the disjunction effect, which on the contrary is an example of the second class of errors, so decision-making errors. Just to give you an idea, the famous prisoner dilemma is an example of a disjunction effect, hence of a decision-making error. Sorry. So now the existence of this kind of situations has two implications in particular. First of all, the most natural set, what seems to us the most natural set theoretic models of cognition cannot be generally used to represent in their generality human judgments and decisions. But also, since these, let's say, structures, set theoretic structures, are the building blocks of logic and probability theory, it is difficult to interpret human judgments and decisions in terms of logical processes. It becomes a problem. Now, there is a well-known research program which tries to solve these kind of problems, cognitive problems, which can be traced back to the work of Kahneman and Tversky. They consider these deviations of classicality as true errors, as true fallacies of human reasoning. And they provide an elaborated theory, which they call which is based on heuristics and judgment biases, to cope with these classically problematical situations. Daniel Kahneman received the Nobel Prize in Economic Sciences because he was the first to integrate psychological insights into economic science. And indeed, he founded what we now call behavioral economics. Of course, this approach is successful. From our point of view, a major limitation of it is that, though intuitively reasonable, it does not offer a unified view in which incorporate all these processes. In particular, we don't know the kind of mental processes which would underlie their theory. So it works well at a descriptive level, probably it works less well at an explanatory level. And it does not offer a unitary view. But there is an element which is important for us in their approach. The fact that they already weaken the mathematical representation of events. They don't use a Kolmogorovian model of probability. Their model is already non-Kolmogorovian because it's non-additive. They call this model capacity. I'm not an expert of capacities because I've studied another type of probabilistic calculus. And so let me come to what I would like to present to you, which is the quantum cognition research program. We know, and we would agree, that quantum theory is one of the most successful theoretical achievements that humans have ever produced. It was originally elaborated to cope with some phenomena where empirical results did not agree with the predictions of classical physics, but quantum theory nowadays is applied to any conceivable scale, from the micro world to living matter. If we think to the phenomena of superfluidity, of superconductivity, which are macroscopic phenomena, we realize so the scale at which we currently apply quantum theory. We also know that it is formulated in a quite complex, I would say complicated mathematical language that uses specific structures that are called Hilbert spaces. So it has its specific recipes to deal with these structures. So unit vectors, self-adjoint operators, unitary dynamics, and so on. These structures give rise to specifically non-classical algebraic and probabilistic structures. So quantum theory introduces non-Boolean lattices, non-distributive lattices, for example, non-Kolmogorovian probabilities, specifically non-Kolmogorovian probabilities, non-commutative algebras, and so on. So, in addition, quantum effects like contextuality, entanglement, interference, non-locality, indistinguishability do not have a classical counterpart. Of course, then one could think, just abstractly speaking, that because of their flexibility, of their generality, quantum structures in Hilbert space could provide the mathematical tools to deal with this classically problematical phenomenology. So I'm just pointing it as a theoretical possibility, okay? This has been the case. So quantum mathematical structures, so detached from their physical interpretation, have been applied since the 90s of the previous century to a variety of phenomena: psychology, economics and finance, biology, computer science, and so on. And this has in particular attracted the interest of funding institutions, but also of media and popular science. And if you Google quantum cognition, you will find some articles and newspapers that talk about this research program. For example, the bottom right, which is in Italian, I think appeared on La Repubblica some years ago. Okay, so what I would like to do is to present a unitary theoretical framework in which judgments and decisions are described as intrinsically non-deterministic, context-dependent processes. So what I would like to do is to give you arguments, serious arguments, to apply quantum theory in Hilbert space as a general theory and a unitary theory for these processes, for these classically unexplainable phenomena. This is something I've done in collaboration with Brussels. This is why we call it Brussels-Leicester approach. Now, this is the analogy I would like to stress here. So in any judgment or decision, which are concrete processes, exactly as in a quantum measurement process, we have a contextual influence where one outcome is actualized from a set of possible outcomes. You know what you do with on an electron to make a measurement on an electron. So you prepare it by a macroscopic apparatus at the end of which the electron is in a precise initial state. Then the electron undergoes a measurement process, so it enters another macroscopic apparatus. In some way, the electron interacts with the apparatus and the electron comes out in a final state. Generally speaking, we don't know this final state. We have only a set of possible states, and the most we know is the probability of each of these final states, unless we are in a very specific situations, you know, eigenstates and so on. So we have that a quantum measurement process is an intrinsically non-deterministic context-dependent process. We think that a judgment is a process of this kind, where the type of interaction occurs not at a physical level, of course, it occurs at a conceptual level, but it is a process of this kind. I just add the remark, probably this is not the proper place where to put this remark. I apologize in advance for this. I didn't know where to put it because without entering into details. But unlike the Tversky-Kahneman research program, our research program, let's say, does not consider these deviations from classicality that we have in judgments and decisions as fallacies of reasoning. We think that there is a different kind of reasoning which overlaps with the logical one. So they are the consequence of a different type of reasoning, a different layer, which we call the conceptual or emergent. So this is a type of reasoning when we create new entities, in some sense, new conceptual entities. But I will come back to this. So the idea is that consider a cognitive test. So we have a sample of participants who are asked to, in this test, to make a judgment or take a decision. At this stage, we don't distinguish between them. Typically, what they do is they write their responses on a paper. No? So they pick an answer from a list on a questionnaire, on a structured questionnaire where they have different alternatives. So the test, which corresponds to what we would call a measurement, is performed, of course, not in a physical laboratory, but in a psychology laboratory. So we try to make the analogy as close as possible as physics. So the participant enter the psychology laboratory where the participant has the questionnaire. It is a space-temporal domain, no? Right? And so the participant has to take note, has to give an answer. Now, the questionnaire contains information because you have, when you design the test, you have to prepare something, right? So you have to explain what the participant is going to do. So the information contained in the questionnaire, which has a meaning content about the situation, which is the object of the decision, defines for us a preparation procedure of a conceptual entity A. So at the end of which we say, okay, this conceptual entity is in an initial state, PA. But then the participant, each participant interacts with the questionnaire, with what is written in the questionnaire, and gives an answer. So chooses, picks an answer. So changing in this way the initial state PA into a new state in a way which is non-deterministic, because we cannot control what the participant will, how the participant will react, will answer. So in a way which is non-controllable or predictable in advance. The only thing we know is when we collect a large number of answers, okay, of responses, and we know the probability, the statistics of the relative frequency of positive outcomes, of certain outcomes. So the participant acts as a measurement context for, let's say, the conceptual entity under investigation. So changing its state in a way that cannot be controlled if not at a probabilistic level. So the idea we try to convey is that a conceptual entity, a concept, a conceptual combination, a decision entity, can be in different states. So are entities non-physical, but they can be in different states and which may change in a non-deterministic way under the effect of a context. So from the researcher who is involved in the foundations of quantum theory, this is a conceptual entity can be described as a state context property system. But now, and here is my research, my previous research, the research on the foundations of quantum physics and quantum probability has clarified that the Hilbert space formalism of quantum theory is needed for any scope system of this type, independently of its physical origin, of its microphysical origin. Any entity that depends on a context when you have an intrinsically non-deterministic state change involved by a context needs structurally the Hilbert space formalism that was originally used to deal with quantum entities, with microscopic entities. This is why we think that this is the case, it is the case to apply the Hilbert space formalism of quantum theory to conceptual entities. So what we do is very simple. Once you have a given cognitive phenomenon under study, and in this phenomenon you identify the entity, the states, the context, and the statistics of outcomes, then you use the canonical prescriptions of quantum theory to represent these entities. We say canonically because quantum theory knows well how to represent states, context, properties, and so on. So then the models we elaborate, the quantum, what we call quantum models, are a natural consequence of these assumptions. And I would like to apply these to a couple of known situations which are long-standing situations which are classically problematical. I will start by an old problem, which is the combination of natural concepts. the issue of what a concept is and how people categorize and combine concepts have intrigued philosophers and cognitive scientists for a long time. So there is the so-called classical view of concepts, which can be traced back to Plato and has been dominant also in cognitive science, not only in philosophy, until at least the 50s of the previous century. Concepts are just definitions. This is the classical view of concepts. So all instances then share a common set of necessary and sufficient defining properties. This is not how we combine concepts. This is something that was already noticed by Wittgenstein. This is not the way we concretely use concepts in practice. There are in particular three empirical characteristics of concepts which do not agree with the classical view. First of all, items are not equally representative or typical of a concept. If we are asked whether we consider apple or plum as more typical than of the concept fruit, well, most of us will probably say apple and not plum. So there are degrees of typicality. Another thing, the membership of an item to a concept is not a yes or no answer. So it is a graded notion. Take, for example, tomato and the concept fruit. Well, a test with where different responses are collected will only give a probability of judgment, which express the probability that a tomato is judged as a member of fruit. By the way, this probability of membership in psychology has a name. It is called the membership weight. Another characteristic, the typicality of a concept depends on the context in which the concept is used. Because apple is probably very typical as an example of a fruit, but if we take juicy fruit, then people would probably answer orange more than apple as the most typical example of fruit. So it is a context-dependent phenomenon. Now, to account for these characteristics, many theories of concepts have been proposed. One of the most known is Roche's prototype theory, but there are other exemplar theory, and so on. The problem is that none of these theories is able to explain how, given two simple concepts like fruits and vegetables, we can form the combination of them. We can form the conjunction, fruits and vegetables, or the disjunction, fruits or vegetables. The first, the combination problem was systematically identified by James Hampton. James Hampton is an experimental psychologist at the City University of London. In the late 80s, he performed a series of membership tests of categorization on both the conjunction and the disjunction of two concepts. Let's briefly sketch what he did. Take again fruits, vegetables, so two simple concepts. Take the conjunction, fruits and vegetables. Take the disjunction, fruits or vegetables. Then consider different items in a list. Apple, tomato, broccoli, olive, coconut, almond, raisin, acorn, and so on. When 24 he took for each pair of concepts. Then, in a membership test, he asked participants to indicate whether they considered each of these items a member of fruits, a member of vegetables, a member of fruits or vegetables. This is a standard in psychology. There is a very refined way to put the answers, which is the Likert scale. Here I considered just, you see, olive with respect to fruits, vegetables, fruits or vegetables, okay? But we can do something that is very simple. Just say yes or no, okay? So you collect the relative frequencies of positive responses. You suppose that the sample is sufficiently large, and so these relative frequencies can be interpreted as probabilities of membership or membership weights, as they call them. Well, Hampton collected the membership weights of several items, taking different pairs of concepts, conjunction and disjunction, and he found significant deviations from classical set theoretic structures. He even introduced a terminology for such deviations, to classify such deviations. Let us generalize for a moment. Let's denote an item by X. Then let's call mu A, mu B, mu A and B, mu A or B, so 4 probabilities, that correspond to the membership weights of the item X with respect to the concepts A, B. When he found that mu A and B is greater than mu A or greater than mu B, he called the item overextended with respect to the conjunction. Of course, you have a violation of the monotonicity law here. In the case you have overextension, right? Because you are judging mu A and B as greater than either mu A or mu B or both. If you judge both, then you have a stronger violation, which is called the double overextension. The same for underextension. If he found that when he found that mu A or B is less than mu A or less than mu B, he called the item underextended with respect to the disjunction. So underextension corresponds to a violation of the law of monotonicity for the disjunction. And you can also have double underextension, so you have a stronger effect. Here I just give you a couple of examples, one for the conjunction and one for the disjunction. You take a razor and you ask people to judge membership of a razor with respect to weapons, with respect to tools, with respect to weapons and tools. This is 0.83, which is greater than both 0.63 and 0.68, indicates that the razor is double overextended with respect to the conjunction. So this means that this triple cannot be represented in a Kolmogorodian probability model because it violates the law of monotonicity for the conjunction. I considered an example for the disjunction. Well, it's the same story. I will not repeat it. So we have a problem. So which was identified systematically by Hampton. What we did in collaboration with Brussels is better classifying the deviations that Hampton found. So we got all the data by Hampton, and we tried to find generally necessary and sufficient conditions for representing membership weights in a Kolmogorovian model of probability. So we wondered, given an item X and membership weights mu A, mu B, mu A and B, so we are working only on the conjunction. When can we say that these data can be represented in a Kolmogorovian model of probability? Well, the definition is trivial. We just need a sigma algebra and a Kolmogorovian probability measure which reproduce these membership weights. Well, we found two conditions, not only one, that are together sufficient. They are both necessary. One of them is the law of monotonicity, which of course does not come unexpected. The other is another condition which we call the Kolmogorovian conjunction factor, this second inequality. So the deviation from classicality identified by Hampton's data goes beyond underextension or overextension. It is a structural violation. The same we did for the disjunction of two events. So we wondered, given a generic item X and mu A, mu B, mu A or B, membership weights, under which conditions they can be represented in a Kolmogorovian probability model. And we found again that we need the law of monotonicity for the disjunction together with another law, which we call the Kolmogorovian disjunction factor. Just to give you an idea, olive, which was tested by Hampton with respect to fruits, vegetables, and fruits or vegetables, gives these numbers. You see, in this case, we are talking about the disjunction. 0.80 correctly is about 0.50 and 0.10. So we don't have a violation of monotonicity for the disjunction. But this is still non-classical because the second law is violated. We said that it's too overextended, too much. So again, olive cannot be represented within Kolmogorovian probability. So we used our general approach, which we call the quantum theoretic framework, to represent concepts and their combinations. And you will see that it's trivial. The application is trivial. Because let's again take an item X, two concepts A and B, the conjunction A and B. Then we take the membership weights, mu A, mu B, mu A and B. How do we represent them in a quantum theoretic framework? Well, we know that concepts are entities in a state. So these states will be represented by unit vectors of a Hilbert space. A, B are represented, I'm using Dirac notation, by unitary vectors. How then we represent the conjunction, the state of the conjunction? By the linear combination. By the linear combination. I even considered, took very simple example of linear combination with equal weights. So the state of the conjunction of two concepts is a superposition state of the states of the individual concepts. How do we represent then the judgment measurement? Measurements in quantum theory are represented by projection operators, orthogonal projection operators, better by spectral families. Okay, so we represent them by projection operators, by spectral families. So how do we represent membership weights? They are probabilities of membership. We use the canonical prescription of quantum theory, which is Born rule. Okay? We do our homework and we find that the membership weight of A and B of the item X with respect to the conjunction is this arithmetic average 1/2 mu A plus mu B plus a term which comes from the superposition. So this, you will have immediately recognized, is the interference term that we find in the double slit experiment. And we proceed in the same way for the disjunction. I'm not going to repeat. What is different with respect to the conjunction is the form of this interference term. But the rest is the same, is just the same. In these cases, once one has a general Hilbert space representation, one needs a specific construction, right? And the exact Hilbert space in which you represent all data is given by the phenomenology. Think, for example, to the spin, where you have two outcomes. One can prove, and it is represented by C2. In this case, one can show that the simplest Hilbert space where you can do the job is the Hilbert space C3, which is given by the ordered triples of complex numbers. So we constructed an explicit Hilbert space representation in C3. It's just a bit of mathematics. But you see, we found an interference angle. Again, this resembles the double slit experiment. You see, there is an interference angle, which I denoted here by theta c for the conjunction, and there is an interference term for the disjunction, theta d. An interesting thing is that this model can also be applied to negations. We don't need to change anything. We just apply it to conceptual negations, and it works. So it reproduces several data sets, not only those originally elaborated by Hampton, but it is important because it does not limit itself to reproduce data, but it finds explicit relationship which have to be satisfied by membership weights for the model to work. So it does not work for any triple of numbers mu A, mu B, mu A, and B. No. In addition, as we will see, it provides new predictions which were not tested by Hampton and which we tested ourselves. So the model is, let's say, if we want to use let's say, a naive notion of falsifiability, the model is falsifiable. Physicists like this, that models are falsifiable, so they allow to make predictions. Okay, so I just give you some examples. Razor, which was double overextended with respect to the conjunction, can be represented, you see, for an interference angle of 64 degrees. So it's like weapons and tools constructively interfere in the conjunction. Okay, if we want to give an intuition for what occurs. This is the other example, Kerry, with respect to spices, herbs, and spices or herbs. Again, for the disjunction, this was under extended with respect to the disjunction, and Kerry can be represented as well. I took other examples where you have a strong double overextension or strong double underextension. So the model can be stretched as we wish, and it still works. Pierluigi, I don't know how much time I have because I don't know at what time I did start.
10 minutes again, it's okay.
How many?
10 minutes, it's okay.
10?
15 minutes, it's okay.
Okay, thank you. Right, so let me just conclude this part on concepts and apply the model to the so-called Linda story problem, then I will stop. So the quantum theoretic framework we have elaborated for the conjunction and the disjunction of two concepts works in a Hilbert space. It does not reproduce all of Hampton's data. It fails in some cases. And we identified the reason for this. So we elaborated, let's say, a generalized model which uses Fock spaces, which are specific types of Hilbert spaces. These are specifically used in quantum field theory. I don't enter into details because the model we have elaborated for the point of view of a quantum physicist is very simple. It is at the level of quantum the complexity of simplest quantum computation or quantum information. So we work on a finite dimension, Hilbert spaces, so it's very simple. And it allows already to infer some interesting results. First of all, we see that some, let's say, quantum effects appear in the combination of concepts. Contextuality, we have context dependence. We have interference, we have seen that superposition. But there is a new one, which is very nice, and it is emergence. You know that in quantum physics, if you take two orthogonal states and you take the linear combination, the superposition of these two states, in this state you have new properties emerging, which were not present in the initial states. Okay, you have emergence of new properties, and vice versa. So you have actualization, emergence of new properties, and vice versa, properties which were actual in the original, in one of the original states, become potential in the new state. The same thing we have in concepts. We did this in a test. So let's take Olive. Hampton tested membership of Olive with respect to fruits, to vegetables, to fruits or vegetables. And he found the numbers that are on the left of this panel. Okay, these numbers we have already seen. We did a test similar to Hampton, but instead of testing fruits, vegetables, and the disjunction, we tested the membership of Olive with respect to fruits, vegetables, and the conjunction. Okay, and compared these results. Well, if we look at data and we leave aside, let's say, the numerical differences for the individual concepts, I will come back to this in a moment, you find that in the disjunction, you have non-classicality. We have seen this. In the case of the conjunction, we have double overextension. Okay? So in both cases, we have non-classicality. But what is interesting for us is that mu A or B and mu A and B do not differ too much each other. They are very close each other. I was mentioning that the membership weights of individual concepts is not relevant because you see, it's not important for us to know whether people are right in saying that tomato is a fruit or tomato is a vegetable. This is not what we want to do. Okay, it may be a linguistic problem depending on the language in which the test is formulated. What is important for us is how mu A and mu B are related to mu A and B, or to mu A or B. This is the real issue, not whether people are judging correctly membership of an item with respect to a concept. Okay. So what we found is that we found similar weights for the conjunction and the disjunction. So from this, it seems, this for us seems to indicate that situations exist where people do not really take into account whether we are using the connective or the connective and in the combination. But it seems like people are judging for certain items, not for all items, but for certain items, they are judging membership of the item with respect to the combined concepts taken as a whole, as a new emergent concepts. We call the process, so we have conceptual emergence, and we call the process of creation of new concepts conceptual reasoning or emergent reasoning. Of course, in many cases, we use, and in certain disciplines for sure, we use logical reasoning. So we use the connective in a proper way, but not in all cases. Combining concepts, and generally speaking, in what goes under the term cognitive fallacies, we think that the other process works. So when we adopt a different way of combining entities, of combining concepts, which we have called conceptual or emergent reasoning. So this ends the part related to concepts. And before coming to the Linda story problem, this is a representation of some empirical data. One would think that this is a representation of the double slit experiment, right? With photons or with electrons, even with photons in the, for example, it would be easier to show. No, these are what is on the plot are the items considered by Hampton in his experiment on fruits or vegetables. You see, we have an impressive effect of interference, which can be seen here. We published this in Behavioral and Brain Sciences, which is an outstanding journal in psychology. But this is quite funny, and I wanted to share this picture with you. Now, let's consider another example of a probability, and then I will stop, of a probability judgment error that can be explained exactly in the same way by using the same framework. We don't need any new ingredient. In 1983, Tversky and Kahneman discovered an important fallacy through the following story about a liberal woman named Linda. So we know, so this is what is written in the questionnaire, that Linda is 31 years old. She's single, outspoken, and very bright. She majored in philosophy. And as a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Then participants were asked to indicate which of the following alternatives they judged as more likely. Linda is a bank teller, Linda is a bank teller, and is active in the feminist movement. Well, 85% of the participants indicated that the second option, where a conjunction is present, is more likely than the first option. So you have an impressive violation of the law of monotonicity for the conjunction. This is an example of a probability judgment error, which goes under the name of conjunction fallacy. It goes without saying that if we do a similar test, we also get a disjunction fallacy. You see, we find that mu A or B, so the judged probability that Linda is a feminist or a bank teller, which in this test is 0.60, is less than the judged probability that Linda is a feminist, which is 0.83. So in a test, we can find both fallacies, both a conjunction fallacy, so a violation of monotonicity for the conjunction, and a disjunction fallacy, so a violation of the law of monotonicity for the disjunction. This is quite standard result, so it has been found in many, many different ways and many tests. There are different explanations. Tversky and Kahneman, so they introduced the heuristics of representativeness, the misunderstanding explanation. My friend Jerome Busemeyer proposed the quantum probability explanation, and so on. There are different, let's say, controversial aspects in these explanations. Our explanation is borrowed from concept combinations, in the sense that a conjunctive fallacy or a disjunctive fallacy are nothing but an overextension or underextension effect. So they can be easily represented in the quantum theoretic framework. We don't need a new mathematics. We don't need a new explanation. We consider them as effects of overextension and underextension. So we explain them in terms of interference and superposition and context dependence. So we borrow the terminology. So the probability, the terminology of concept theory. So mu A, which is the membership weight of, mu A is the probability that Linda is judged as a good example, is judged as a feminist. Mu B is the probability that Linda is judged as bank teller. Mu A and B, the probability that Linda is judged feminist and bank teller, and mu A or B, the probability that Linda is judged as feminist or bank teller. These become membership weights of the item Linda with respect to the concepts of feminist, bank teller, feminist and bank teller, feminist or bank teller. And it works. It's as you can see immediately, we get the result. We can reproduce the data of Tversky and Kahneman, but also of the successive tests. We have several tests for which the model works, which it's even more successful than the model of Hampton, the representation of the data of Hampton. So we have the fact that feminist and bank teller destructively interfere in the conjunction and constructively interfere in the disjunction. And the conjunction and disjunction fallacy in decision theory as just the decision theoretic counterparts of over and under extension effects in concept theory. We predict also double conjunction fallacies, which are less likely, but they do exist. The model predicts double disjunction fallacies, so exactly like in concept theory. Okay, so this I will skip because the quantum theoretic framework we have elaborated for human judgments also work for human decisions, where you have disjunction effect, like in the prisoner dilemma. Other violations are known, go under the so-called Ellsberg type paradoxes, where you have a violation of expected utility theory. And again, the same quantum theoretic framework works. We don't have to change the representation and so on. So my last slide is the following. So we have tried to address the question of quantum theory as a general theory for human cognition. So the problem of how and why we are justified in applying quantum models in cognitive domains independently of their empirical effectiveness. We have worked out a theoretical framework which is unitary, which is inspired by the foundations of quantum physics to represent in Hilbert space the phenomenology of human judgments and the decisions under uncertainty. A cognitive test is described exactly as a quantum measurement process, as a two-step process, which involves a preparation and a measurement on a conceptual entity, while the participant operates in the test as a context for the entity which changes its state. Whenever the conceptual entities, its states, context and properties and statistical relations are identified in the representation of a given phenomenon, the quantum theoretic framework consists in making explicit the usual Hilbert space representation of entities, states, context, properties, probabilities, and dynamics. This was applied to long-standing cognitive fallacies. Ellsberg paradox is 1961. The first studies of Roche are of the 70s, so they are quite old, these fallacies, but the theory can be applied, provides prescriptions to be applied to any, in principle, to any judgment and decision. Here I just report some references. These are, well, these are mainly manuals. There is this nice article, which is a review article, which appeared in Synthese by Blutner and Weingraben on the links between quantum cognition and bounded rationality. Then there are other manuals that are well done and complete, in particular the one by Busemeyer and Brusa and the one by Haven and Krennikov. The manual of Hampton is more standard in some sense. While these are my the publications resulting from my research in collaboration, in particular with the Free University of Brussels, this does not go under physics journals. It was published by economics journals, by psychology journals, by philosophy journals, physics journals, computer science journals. And this was important for us because what we do is not bounded to a single discipline, but is interdisciplinary in spirit. Many thanks for your attention. I don't know whether I bothered you more than what I should have done. I apologize in advance if so, but I'm ready to take your questions. Thank you very much.